to proceed is to actually replace the function by a majorant or by a minorant, thus generating an inequality. And you want this majorant to have some nice properties. And for this particular problem, it happens that the nice properties that we need, for example, are that the Fourier transform is compactly supported. Because you have a function here, you have an infinite sum here at the bottom that involves the Fourier transform of phi, especially if this phi has a compactly supported Fourier transform, this would make your life much simpler. Right? And also you have a phi hat of 0 there, so you want to not change that much. So the idea here is to just replace your function g by a major m of exponential type delta, so I'm calling here m delta, major of exponential type 2 pi delta. So let's say Fourier transform is supported minus delta delta. Well, if you have this major, then you can replace g by m hat, and then you can use the explicit formula to now sum this m hat, right? And the rest of the proof here is just careful asymptotic analysis of this term, right? You will have to use the qualitative description of m to evaluate these two terms, and here there is an integral involved the logarithm derivative of the gamma function you have to use too. So this last one you use the information about the Fourier transform of m hat and partial summation and the prime number theorem to evaluate this. It turns out that the main term will come from this integral here involving the gamma function. All the other terms will be error. At the end, you have to choose your parameter delta, the support of the Fourier transform. You have to choose it correctly. You have to choose it in terms of the t. Right. But this is the main idea of the proof. Now, the question comes up. Well, you gave me a nice, varied method on the first part of the talk. But the method was not very, explicit. You just said that you can put for Gaussian or the truncated Gaussian, and you said this was powerful because you could integrate against some measures. But now I have three explicit functions here that need to be taken care of. And you do this with your method. Is your method robust enough to cover these three functions? And the answer is yes. And I'm presenting to you here how we can integrate the Gaussian against certain finite measures to produce these three functions. So, for example, the second function g, arctangent of 1 over x minus x over 1 plus x squared, is the integral of the sine Gaussian. This is a log function against a certain measure of lambda, and the measure of lambda is limited. And believe me, this is a finite measure in non-negative. Right? Same thing happens for the h function, and for the f function, this is a simpler measure. Well, that goes to this application. And then my part 3 is I should to give a brief account of what we have been doing recently. This is a recent work that I did with Faishan-D, Friedrich Schlickman, and Michael Milinovic on this sort of extreme problem with Fourier analysis related to the pair correlation of the zeros of the Riemann zeta function. So not to bore you, just talk quickly over the last 10 minutes. The setup is the same. Z is a function here. The zeros are denoted by rho sigma plus I gamma, generic 0. We have the zero counting function. The zero counting function counts the number of zeros up to height t. And it's well known since the time of Riemann that the number of zeros at height t is approximately t log t over 2 pi. The goal, and this started with Montgomery, was to study the pair correlation function, which is n of t. I give a parameter beta, which is to count the number of pairs of zeros. I'm just labeling here the ordinates. Number of pairs of ordinates of zeros, gamma and gamma prime, between 0 and t, such that the difference gamma prime minus gamma is at most 2 pi beta log t. Why? What is this number? Why do we have this 2 pi beta log t? This is just a normalization. So what I'm counting here is since the number of zeros at the height t is t log t over 2 pi, what I'm counting here is the number of pairs of zeros that are less than beta times the average spacing. So this would be the average spacing at height t, right? This counts the number of pairs of ordinates whose difference is less than or equal to beta times the average spacing. Well, in 1972, Montgomery conjectured that this n of t beta is approximately the number of zeros at height t times a certain factor. Integral from 0 to beta 1 minus this measure dx. This somehow suggests that the zeros are not equally distributed. If the zeros were equally distributed at all heights, this pair correlation function would not see this term. It would just be equal to the n of t. Right? So this suggests that it's somehow well, if you note that, and then you note the asymptotic of this when beta goes to infinity, right? The integral from 0 to beta of this measure is approximately beta minus a half plus the term of 1 over beta plus the goal of 1 over beta squared. So we want to find, the goal here is to find bounds for this object, say 15 beta when t goes to infinity that somehow look like this. Right? And here's the measure of interest, right? So here's the picture of these guys. This is a famous story of Clotilde's meeting over the T-time at the Institute in 1972 when Montgomery, who was a graduate student, went to Princeton to show his results, and he was suggested to talk to Freeman Dyson and show his what he had found about this kernel 1 minus sine pi x over pi x squared. And then Freeman Dyson was the one who recognized this kernel and said, hey, this is the same kernel that appears in my computations with random matrix theory. Right? This is the percolation function for the eigenvalues of random matrix, random permutation matrix. And this was the birth of this whole connection between number theory and random matrix theory, which gives a lot of jobs to many people today. Which I find it very nice. So, the goal that we had in mind here was to somehow improve this old classical paper of Gallagher in 1985 on I was on the Cornell journal. He found, so he considered these two quantities, the lean soup. So this beta considered the lean soup of NC beta over n of t and the lean mean of NC beta over n of t, and then he proved that assuming RH, so here is all conditional, for beta half a natural, you have that u of beta is less than this, and you have to put a technical assumption here, almost all zeros are simple, then you have that the lower bound is bigger than beta minus 1 plus the error term. Remember that the true value should be beta plus 1 half. Right? So here he's giving 1 half up and taking 1 half down. And he proved this just for beta natural number. What was his idea to prove this? So Montgomery found a formula, and again, this might be evaluate somehow the correlation of zeros when you plug in a test function r, and there's a certain weight here. So Poisson curve knows the weight. But if you plug in a certain test function r, and evaluate the gamma prime minus gamma multiplied by the normalized factor and take the limit, this is going to give you r of 0 plus this guy. So the Montgomery found that this was only true for a function r, which was integrable with Fourier transform supporting minus 1, 1. So if you could plug in the characteristic function of the interval minus beta beta on this formula, this would give you the correlation conjecture. But you cannot plug in the characteristic function of an interval there. You can only plug in functions that have Fourier transform supporting minus 1, 1. So what Gallagher did was to, well, I cannot plug in the characteristic function of the interval. This is the function that would give me the conjecture, but I can plug a major and a minor of the characteristic function of the interval. And of course I want to choose this guy as good as possible. And as good as possible means